Yes, I'm Bryan Walsh. I'm the future correspondent at Axios, and I'm really happy to be here at Q2B 2020 to talk about this really important subject. I mean, it's incredibly vital, the idea of using quantum computers, which can simulate nature at the most fundamental level, to use it in a way to both better understand effects like climate change, but also find new materials, new methods that can help us actually solve this incredibly important problem. So we have a great panel here. Jean-Francois Bobier is the partner and associate director for technology advantage at Boston Consulting Group. Michael Marthaler is the managing director of HQS Quantum Simulations. And Mark Daly is a digital industry associate at Bloomberg New Energy Finance. So, I want to start with you, Jean-Francois. You've been involved in some BCG research that really looks at where quantum can make the biggest difference on sustainability. So maybe we can just start by having you sort of talk about that research and point us in the directions of what can really make a difference here when we're talking about quantum and sustainability.
So thank you, Brian. So indeed, we conducted a research last year that we published in January this year, and we looked at how quantum computing could help fight climate change. Basically, what we did, we tried to position use cases on two axes. One would be the combined impact. So this is the CO2 baseline that we are looking at. So for example, people talk a lot about planes, but when you look at the CO2 share of planes, it's only 2%. There are emissions that are much higher, and so we need to when we look at use cases, we need to consider, of course, the level of CO2 we are looking at. And then we looked at, based on the technology roadmap that we know or we can imagine, when we could have an impact. And so we came with a 2x2 matrix, and we basically came up with a list of use cases where we believe quantum could have a high impact. As you mentioned, the most important thing about quantum computing is the fact that when Richard Feynman introduced it, he said basically if you want to simulate nature, you need a quantum computer to do that. Mm-hmm. It's not a surprise to see that the most important use cases that we found are actually based on that capability, the capability to simulate nature. So basically to use the quantum chip as a lab where you do the experiments. Because, for example, if you take, fertilizer production, we still use a process today called Haber-Bosch that was found a century ago. When you think about it, for 1 century, even with the best technology that we have today, with all the computers and all the nice algorithms we have today, we have not been able to find a better way to produce fertilizer than a process that was found a century ago. And there is a simple reason why, is because today we find those things through trial and error in lab, and it takes time. The promise of quantum computer is actually to basically to put the lab in a chip and to do the simulation on the chip and to try and to understand many things. So when we did this research, we found that there are, as you know, there are two eras for quantum computing that we are looking at. The first era is called NISQ, so which is the short-term computer that we'll have probably during the next decade until 2030. So those computers will have many qubits. They will actually double every year or so, but they will have errors. They will not be perfect. So the N from this comes from noise. But we can still do interesting things with those computers, especially when it comes to molecular simulation. And what we found very interesting is that we could look at what is called catalysts. So basically, relatively small chemical compounds that enable chemical reactions. And for example, I talked about fertilizers. You probably don't know, but today, to produce fertilizers, we consume more CO2 than we do with the aviation industry, the entire aviation industry. And of course, we need to feed 7 billion people with those fertilizers, so it's a very important use case. But we know today that nature is able to produce those fertilizers for free, without using CO2. It uses a process called nitrogenase. It's a natural process, but we still don't understand quite well how it works and how we could scale it in a factory setting. With a quantum computer, we could look at how it plays out and try to repeat the critical steps and to scale it industrially. That would be a massive use case because it would be already 2 to 3% of CO2 emissions. Of course, there are other catalysts that are interesting. So, for example, there are catalysts that are used in batteries. As you know, energy storage is very important because now we are good at producing energy through renewables, but the problem with renewable energy is that it's not constant. You might have wind and then you might not have wind, the same with solar and so on. So being able to store power is very important. And we know we have still a lot of progress to make in density for energy storage. So being able to store energy would be a game changer. Another thing that would be short term, in the next decade, would be around carbon capture. Because as you know, we have also the problem of all the carbon that we have emitted so far. And if we really want to shift the balance, we need to be able to reverse that somehow. So carbon capture will be very important. And there are technologies around that. And then, but we can talk to this later, there are use cases that we see after NIST, so after 2030. So for example, around new materials. Designing new materials is very complex because you need to optimize around an important set of constraints. So you want, for example, cement that is light, that is that resist to rain and outside conditions, that of course isolates very well. But we think that those use cases will happen later because it would require much more stability and much more computing power.
I want to go to Michael, and thank you, Jean-Francois. That was a great intro to all the ways we can potentially employ this technology. One thing I'm particularly interested in for you, Michael, is quantum simulation and modeling when it comes to climate change. This is an incredibly complex system, the climate. We need to know where it's going to go decades ahead. How can quantum computing make a difference at that stage?
Yeah, thanks. Good question. In principle, we know that quantum computers could potentially be used for all types of simulations that are called often finite element simulation, meaning you want to simulate the climate and divide the space that you're simulating into small parts and then kind of simulate how airflow and so on goes through these different grid points that you have defined. And we do clearly have an idea that quantum computers could be really powerful in doing this. But this is not something that's going to work in the so-called NISQ quantum computer that Jean-Francois mentioned. So for this type of applications, we will definitely need the so-called fully universal or fully error-corrected quantum computer. And there's also still quite a few things on a purely algorithmic and software level to be figured out. The algorithms that would be used, there are really good ideas out there, how that would use, and very, very tempting ideas that look really extremely promising. But I would say it's not yet that all the details have really been put in how this really will work. And of course, there's still time. Yeah, the fully universal quantum computer would expect 10 to 15 years. And in that time frame, we would also expect that this type of algorithmic and software questions will be solved. And for us, for example, as a company, currently we favor as a simulation goal this type of molecular and material simulations that Jean-Francois mentioned. But then actually, as we look towards the 15-year timescale, clearly the next big thing for us is this kind of finite element simulations, which could be used to simulate just climate developments, but also for all other type of simulations that are being used already now, but they could be much more powerful, like kind of the wind resistance of a car. You could kind of try to make all types of planes and cars like lighter by designing them better, and all types of questions that could be done with this type of simulation software.
That's excellent, Mark. Kind of maybe something that brings together these two areas. You had mentioned earlier in our sort of pre-discussion about the role of quantum in optimizing power systems. It's going to be increasingly important as our power systems grow more complex, as intermittent renewables become a bigger part of how we get energy, as electric vehicles get hooked up into the grid. You're taking an already complex system, making it that much more complex. So again, sort of talk a little bit about, well, how can quantum help with that?
Yeah, so I think sometimes I certainly came into working in clean tech thinking, there's somewhat of a solution to clean power in the world. We have cheap wind, plentiful cheap solar all over the world. It's the cheapest form of generation. But as all these renewables plants are built, something that maybe goes undiscussed is the very small average size of a renewables plant compared to the average gas turbine. So this means if we want to generate the same amount of power, and we're actually going to need to generate more and more power as we electrify, transport, and heat, we're going to have this massive amount of growth in the number of endpoints on the grid. As well as this, we're going to have growth in the number of EVs that can be used as flexible capacity on the grid. And there's also going to be a transition towards electrified heat. So heat pumps are going to be another source of flexibility on the grid. For the next 5 to 10 years, this is not something that the power system can't handle. But as we get to 2030 and beyond, the growth in the sheer number of distributed energy resources really accelerates. So the power of quantum here is basically in help optimizing a system. People are talking about this for logistics operations now, but power system operators don't have very good visibility on these renewable energy resources. They're connected at very low voltages, which they have historically not managed. So they're going to need help predicting who's going to be generating, predicting which EVs will be plugged in, and then optimizing that entire system. This is something actually that E.ON, the German utility, in the recent Innovation Day talked about using quantum-inspired techniques to help them build a vehicle-to-grid charging operation effectively. And they claimed that it has been quite successful using quantum-inspired techniques. So adding flexibility in the power system in this way is going to be really important in achieving deep decarbonization of the power system. You can achieve 50 to 60% renewables without running into too many problems. But at a certain point, you're going to need to add storage if we want dispatchable power. So the interesting thing about this problem as well is it kind of the timeline of when this becomes a big issue for power system operators is on the decade scale. So it's maybe something that quantum computers can kind of evolve in tandem with.
That's a really good point. I mean, you look for problems where the time frame actually can work with where quantum might be going, which is not the case for all environmental problems. Some of them coming a lot faster. We got to you, Jean-Francois. You talked a little bit about in the intro about looking for materials, the ability of quantum computers to find materials. One area that I'm particularly interested in is carbon capture. How can we figure out ways to bring carbon out of the atmosphere? Materials are key to that, as they are to things like batteries as well. How do you foresee that being used? I mean, in terms of actually finding materials, finding elements that can actually help us solve those enormous engineering challenges, starting with something like carbon capture, I suppose.
So I think part of the answer, again, starts with nature. Nature is able to capture carbon very efficiently, as you know, in trees, in plants, and everywhere. So one good area to start would be at, again, simulating the molecular reaction that goes on naturally, understand how it works in the critical steps, and try to reproduce it in a factory setting. So that could be a good place to start. The same idea that we have with fertilizer production, actually. So that would be, let's say, the first logical step to do that. As you know, there are two types of carbon capture. So there is one which is capturing carbon from the air. So that would be a good start. And there is another carbon capture which is trying to capture carbon, directly from factories or or plants. And those, for the second part, we will still need to figure out more precisely how could we capture even more carbon and especially store it very efficiently.
Michael, another subject that came up a little bit in the pre-discussion was quantum simulations around fluid dynamics specifically, and that's an area, I'd be honest, that I know that term, but I don't know it well enough. I'd love to hear you go into a little detail about, again, how we can use it in that way.
Yes. Basically, actually, if you talk about simulating the climate, so if you want to make long-term or short-term prediction, weather or climate, this is actually a simulation of fluid dynamics of a specific type. I mean, if you simulate gas or water, of course, is a difference, but the kind of underlying math is actually quite similar. And so this is actually the reason why one of the reasons this is interesting. The other thing, of course, fluid dynamics goes into simulation of kind of the resistance. If you want to make like cars or planes that are very efficient, yeah, so they should like not have too much wind resistance. And this is something where this goes in, and kind of this all can be mathematically mapped to the same type of problem, to kind of problems that is so-called linear equation that you need to solve. And in principle, we know that this should be super, super efficient on a quantum computer. So we should be able to solve this with a huge amount of more kind of precision on a quantum computer than we can do it right now on normal computers. And especially for climate type simulations, this is one of the things where truly people already today use the largest computing centers that we have available. So actually, if you look at the use of huge computing centers, it's two things: this type of climate simulations and this type of quantum mechanical simulations of molecules or reactions that have been discussed before. And so there, having much more powerful simulations could be really cool. Of course, to some extent, it would also be nice to reduce the energy consumption of this type of simulation itself. I'm not sure. I don't think this kind of computing centers really have that much energy consumption as compared to other things like making fertilizer or making cement. But replacing it with a quantum computer, I mean, the quantum computer is also not too cheap in terms of energy, but still much better than a whole supercomputing center. So in that sense, it will also be at least some gain. But here we're talking again 15 to 20 years until this will come.
Mark, continuing on that to a certain extent, looking at thinking about energy being really the key to climate change, you had told me that quantum might be able to deal with or put a dent actually in ICT energy consumption. I'm curious how that would potentially work.
Yeah, so we get a lot of questions from our clients who work in utilities, energy companies, power equipment companies. They see the data center market as a big area of growth for them. In terms of how much of a share of this is our total final energy consumption, it's not on par with cement or steel. So this isn't going to transform the world. I think it's about the study in the US shows about 3% of power consumption is consumed by data centers. I think it might be more impactful in certain regions. So in my native Ireland or Virginia in the US, there's been like clusters of data centers basically because it's suitable climate. There's economies of scale in terms of skilled workforce and telecoms. But in these regions, the capacity of data centers in terms of power consumption can be 15% of peak summer power demand. So I guess the question is, how can quantum cut that? For the high performance computing applications that Michael's been discussing, and also machine learning training is another application where this might cut power. It is hard to actually say how much data center demand is for that versus hosting this Zoom call or your work from a application. There's probably some people in the audience who would know the details on that more than me. But yeah, there's definitely something that could cut into what utilities consider to be a big growth center in terms of power demand.
Mm-hmm. Well, I'm sure, I know this panel is definitely worth all the energy that might be going to actually putting it out there. But Jean-Francois, we've talked about Timeframe a few times here, and sustainability is not a challenge that's going to wait. Climate change is happening, and it's growing with every passing day. At the same time, we're kind of with quantum caught between the lab and those are real-world applications that we're hopefully going to see here. So, how do you make the case for companies that are sort of in there, like that this is actually going to return on your investment, that it's going to be worth investing in this kind of technology, both to obviously achieve these kind of, face up to these challenges, but also all the other areas that quantum can make a difference in?
So that's a question we get very often from our clients, and thank you for this question. It's a very important one, and I think this conference is called Practical Quantum Computing for a good reason. Is because we try to be practical. So when we think about time frame, we tell our clients that nothing practical. I mean, we don't expect what we call quantum advantage, so which is a practical use case to happen in most industries before 3 years from now. So we expect to see a first quantum advantage, practical quantum advantage, between 3 to 5 years from now. And 3 to 5 years might, in the long scheme of things, especially for climate, is okay. But for a company, it's still a long time. Maybe your client, the CEO, might not be there in 3 years, and so he might not want to invest for the next guy after him. It's a clear problem that we are facing. So I think there are a few answers to that. So the first answer is obviously it will give a tremendous advantage to the first movers. For example, if you're in material science and if you are the first to be able to set up a good quantum algorithm and a quantum setting, you might be able to find the first materials. Or if you're a pharma company, you might be able to find the first drugs. And as you know, in material and drugs, you can actually patent what you find. And so you might be able to patent first the interesting compounds. So there is actually a benefit to be first in a way. It's also true in other areas, for example, in finance. So there is a first mover advantage, but still it needs to build over a long period of time. But still, I think we think that's the first reason. The second reason is obviously when quantum will become important, and we all believe, I think, around the table that it will become important. Again, we see the hardware really going in the right direction. We see algorithms, and Michael can tell more about it, also going in the right direction. So we see the conjunction of hardware and software coming nicely together in time. When it will be the case, and again, it's going to be in 3 to 5 years to see the first benefits, there will be a war for talent, and the talent will be scarce, and it's probably the right time now to build expertise, to build knowledge, because when it will be fashionable to be in quantum, all the talent will be allocated elsewhere. Today, the talent pool worldwide is the order of thousands, not more. It's a very small community. And I think there is a third reason also to invest in quantum now, is that obviously some of the clients we are talking to, they also like to be innovative company. And I think there is you can argue that there is a return on investment to do quantum experiments, to share them with the public, to excite the imagination. And we see some companies, for example, Volkswagen, for example, that use quantum computing as a very good avenue to show that they are an innovative company. The problems that they are solving right now are not real problems, right? So, for example, they showed proof of concept to simulate the traffic in Shanghai, but they do it with a few hundred cars and in very specific conditions. So it's not very practical, but still, it's a step in the right direction. And I think it creates a nice image for Volkswagen around innovation.
That's great. And what you said before about the ROI is so key to climate change, because having reported on this subject for a long time, that disconnect between a company's need for returns on a certain time frame versus obviously the longer term aspect of climate change is so important. And then, Mike, I wanted to go to you. I think perhaps the last question, because we're kind of running out of time. We focus a lot on the hardware of quantum, the software as well, the algorithms. But as Jean-Francois said, I mean, it's people, it's talent that actually do this. So, how big a barrier is that small talent pool that Jean-Francois mentioned? And then, what can be done hopefully to build that, so again, we can make a difference on the kind of climate timeframe that we need to do?
To some extent, and in some areas that are needed for this kind of work, the talent pool is small. But you can bring in people also from other areas. And as we improve, like the software stack, not everybody who works in the vicinity of this topic has to be an absolute expert on everything in quantum computing. So basically, you can build a layer kind of that does the quantum computer, or let's say more of the kind of hardware part of the quantum computing. And then you can start to work with people who have, for example, a chemistry background. Or if you go a little bit more abstract, maybe at some point you can also bring in more people that have a purely like information science background with a good understanding of linear algebra. I think that should be okay. So I think if we use the talent pool that exists, plus expand it a little, but use it to build up lay a solid foundation, so to say, upon which other people can work more and more. I think this should be work out really well.
Hearing you all speak, I mean, climate change is a very tough subject. It can be one where you can be pessimistic quite often, given the scale of the challenge. But I do feel a lot better actually knowing that this kind of technology can be underway, not just to help us actually make a difference, actually help us create those materials that we need, but actually to understand this system, to actually get to the quantum nature, the fundamental quantum nature of reality. So thank you all. Thank you, Jean-Francois. Thank you, Michael. Thank you, Mark, for taking time out of your schedule for this panel. And I think that's a wrap for us. Thanks very much.
Thanks.
Thank you very much.